Here we have a Wimshurst machine, or what's supposed to be a 67,000 volt Wimshurst machine. It's still a work in progress. Right now it's around 200 volts perhaps. We're getting there, but definitely a work in progress. Let's turn on our spotlight here. Oh, okay, there we go. So what is a Wimshurst machine? That is a great question. Let's get into that right now. So a Wimshurst machine is basically, well, it belongs to a class of generators called influence machines. And these influence machines, basically, they separate charge through electrostatic induction or influence. And the Wimshurst machine consists of the two iconic counter-rotating discs and also two Leyden jars, which are capacitors, which store charge. A quick review from physics from last year. Now, most often, a Wimshurst machine is powered by a hand crank, but it can also be powered by an electric motor, for example. Essentially, this Wimshurst machine is a simple high voltage generator, but it is also very low current, and it can be used in many experiments. Now, what experiments you may ask? So these are the experiments that it can power and more. First of all, it can power a smoke precipitator to clean up some smoke. It can power a laser. In the early days, it also powered X-rays. In fact, it also powered the first electron microscope back in 1930s in Germany. Basically, it can power anything that requires high voltage but a low current. And now my Alexa is turning on because I did not say Alexa. Okay, let's continue. So the main parts of the Wimshurst machine. So the Wimshurst machine consists of the disk assembly, which you can see are the yellow things right here. It also has a drive assembly, which you can see has a crank and a drive pulley and an axle. It also has the chassis, which holds everything, and also the electrical assembly, which is not pictured in this diagram from Fusion 360. So the disk assembly. The discs are acrylic, 1/8 inch thick acrylic that are cut using the Epilogue laser cutter in the Wimshurst Tech and Design Hub. These circular acrylic discs are 290 millimeters in diameter, and on it we have 24 aluminum sectors. Now these aluminum sectors essentially are small voltage producing cells from which the charge will be collected later. And how I made these is I 3D printed 24 little sector templates, and I taped these around using a sector spacer that I also made in Fusion 360. Then I cut out a bunch of sectors using the sector templates from aluminum foil tape. Then I taped them on. The center cutting design is actually the version 8. I was going to show you all the previous versions that I have on a small acrylic board, but it seems like I left it at school, which is very unfortunate. The overall cutting is also generation 2, since here we have gen 1, and I failed pretty badly because I first cut out the outer circle, then I took it out, and a few days later I put it back in and cut out the inner circle. So this whole thing is not centered correctly. That means the Wimshurst machine, it will wobble a lot. That's not good. And then we have the bearing assembly. So the bearing assembly is what helps the discs rotate smoothly on the disc axle. So originally I was going to use roller skate wheels and cut a groove out of it and then do something like that, but I had lots of difficulty making a groove, so I decided to design my own bearing assembly. And here we can see a diagram of a cutaway version, a cutaway view of the bearing assembly, and this is a printed version of the bearing assembly, printed using the white resin on the Form 2 in the Wimshurst Tech and Design Hub. So I went through 11 versions of this design, and in these bearing assemblies, I use these types of bearings, also known as 608-2RS bearings. The 2RS basically means there's 2 rubber seals on the outside to help prevent dust and grime and stuff like that. And here I have a couple examples of previous versions. These are all failed versions. For example, with this one was not centered correctly. It had some printing artifacts. This was version 6. This version 7 was one of the working ones. I printed 2 copies, so this is a leftover one. This is one of the earlier versions where I just stuck it directly to the build plate without any supports. That's why it looks separated like this. I think this was my first version actually, and you can see some markings that Dr. P made to help indicate what I can possibly do to secure these to the disk assembly. And how I accomplished that was using hot glue to glue it onto the assembly, and it will be secured using these 4 pins that fit into these holes. Now, the axle. So the axle is the material is acetyl homopolymer, and I bought this from Granger. It is 5/16 inch in diameter, and I threaded the ends myself, and it was very difficult because this material has a very, 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 very low coefficient of friction. So that means every time when I went to thread it, the die would just pop off. And that made it extremely difficult. And it also meant that it's impossible to grip it in anything in a vise unless I wanted to destroy the material and just grip it directly in the vise, which was not good. So I held it between 2 pieces of wood, but that meant it would slip since it has such a low coefficient of friction. So I ended up having to hold it with a pair of pliers. Originally, I used a conductive steel rod as my central axle, and we'll talk about that later because that did give me some difficulties. So the drive assembly. Here's a picture of the completed drive assembly. It's basically this part down here with the crank and the 2 drive pulleys. So the crank is a modified design that I downloaded from Thingiverse. I actually contacted the owner for the design file instead of just the finished file, so I could actually modify it, and he responded pretty quickly actually, and I was pleased with that. And I threaded this using actually reverse threading. Is it reverse? Yes, it is reverse. So usually when you thread something on, you turn it right clockwise for it to become tighter. Well, this is actually different. You turn it counterclockwise for it to become tighter. The reason why I did this is because during operation, that means the handle would tighten onto the steel rod and it wouldn't become loose. How I secured this was, well, this was a very tight fit, and I had to use pliers to twist it on. And then I also used some blue thread locker to make sure it doesn't back off. This crank was actually version 10 of my design, and I ended up printing it with white resin again on the Form 2. Originally, I was planning on using some durable resin. The durable resin has a lower coefficient of friction, meaning I wouldn't lose as much energy to friction. But I had some major difficulties with printing since, well, this is an example of version 8. And you can see I have some big printing artifacts over here. And also with the knob, which is not pictured here, this is what happened with durable. You can see it all looks fine until you look at it from the side, and you can see it's pretty bad. So I ended up using white. And then we have the drive pulleys. I used a 5-spoke design to help evenly distribute the forces, but I don't think that mattered too much since there's barely any force from the drive chain, which we will look at next. I used this design because it was very similar to Dr. P's Wimshurst machine that I borrowed and put in Glimshire and made some measurements. These were originally going to be secured using a pin through the drive shaft, but I decided not to do that since that would make modifying the position very, very difficult. So instead, I secured it using 2 fender washers and squeezing them together on both sides. For example, here's a broken example. I would be squishing these on both sides, and then that would be pressure fit onto the drive shaft, and that worked surprisingly well. This was also printed using white resin, and you can see that there are some slight printing artifacts. For example, you can see some layer lines, but these weren't a big deal because it's just a drive pulley. It doesn't have to be very smooth or anything. Okay, so here we have the drive chain. I used a Buna N material for the O-rings that I bought from online. These O-rings are, the model number is 258. They're Shore 70D hardness, meaning they have around they are harder than erasers, for example, but they have around a similar hardness to a lacrosse ball. And the hardness is a measure of how easily it is punctured or pierced by an object, a metal object usually. The outer or the inner diameter of this is this 5.984 inches. The outer diameter is 6.262 inches. Here's an example of an O-ring that I used. And one of these O-rings is twisted so that I can generate counter rotation. And I explained previously that we want counter rotation so that the sectors move past each other relatively. As we just talked about in special relativity, everything is relative. And if the sectors move together, nothing will happen. And we'll explain why in just a bit. And these O-rings are powered using friction drive, meaning they are friction fit onto these drive pulleys, and it won't be slipping. Yeah, it has a pretty high coefficient of friction. Okay, next we have the chassis. The chassis holds the thing. So the base, we have a big piece of plywood. I mean, it's plywood. There's nothing much to say about it. It's wood. You can burn it. It's pretty thick, yeah. And it also has some posts. And then we come to the supports. So I salvaged these supports from the woodshop scraps pile in the Glimsher Tech and Design Hub to prevent it from being burned. And I don't think that's what would have happened, but it's a physics project. So these supports are around 12 inches long or 12 inches high, since they will be standing upright. And on the bottom around here, I drilled a 7/16 inch hole, and then I inserted some aluminum sleeves to increase reliability and decrease friction. At the top, I have a 5/16 inch hole that is drilled 8.75 inches from the base. This would hold the axle of the disc assembly. And just to specify, the reason why I put aluminum is because we have a steel axle for the drive, and that would not be good for the wood. And these are secured to the plywood using some angle brackets and also the posts from the previous slide. Okay, now we have the Leyden jar supports. So these are two 7-inch tall 5/16 by 18-inch threaded steel rods. I chose to use steel rods because, well, we need electrical conductivity for this, and I will explain why later. I inserted these into 2 drilled holes on opposite sides of the Wimshurst machine, and they're secured using nuts and washers and also a lock washer, like everything else. The electrical stuff, which makes everything go zap, which is what we want. Yes. So first we have the neutralizing bars. And as the name suggests, these neutralizing bars neutralize. And how do they do that? Well, they need to be able to conduct electricity. And you can see there are 2 copper brushes on each side of the neutralizing bar, which makes contact with the aluminum sectors. We will see a diagram later. These are secured onto the acetal threaded axle using nuts and fender washers. What is pictured here is a generation 2 design because it used electrical tape. There's a specific reason why. In generation 3, I eliminated the electrical tape. The alligator clips here, we have one on each side of both of these neutralizing bars. They are soldered on using some regular lead solder, lead and tin. And then we have some solder wick for electrical contact. And then one of the arguably most important parts, but also probably what is not working on mine right now, we have the charge collector combs. I used a couple 1/8 inch copper brazing rods. Oh, and also just to specify, these are also copper brazing rods. For these copper brazing rods, I bent it using a circular cylinder, which is in fact this. Bent it around this to make a curve, U-shaped curve, and then I attached a few or several 22 gauge copper wire, and I soldered them on. You can see in this picture. Then I proceeded to cut these to make some sharp electrical points. Now these actually do not make contact with the sector, and then but they do work somewhat, and we'll explain more later. These are secured onto the Leyden jar supports using fender washers again. Oh, and also just to specify, fender washers are the same as regular washers, just much, much, much bigger. Okay, now we have the discharge electrodes. Discharge electrodes are made out of two 18-inch, 1/8 inch diameter copper brazing rods, as everything else in my electrical assembly is built using. Then I soldered two number 8 by 32 cap nuts on the ends. These discharge electrodes will also be secured onto the Leyden jar supports using fender washers again. I polished the tips of these discharge electrodes using a Dremel and also some Tripoli polish. This would help reduce the unevenness and would maximize the symmetry of the electrical field, which is quite important. Now we have the Leyden jars. So the Leyden jars are made using a PVC lamp protector sleeve, which is this clear stuff you can see in the middle, and then also 2 layers of aluminum foil. There's one on the inside and this one on the outside. These are again secured using a fender washer up here, which you can see is just a normal washer, but bigger. And I made 2 of these. This one you can see is the 0.83 nanofarads one, and the other one is the 0.76 nanofarads. Now you can see that this capacitance is quite small, but it has an extremely high breakdown voltage because PVC has a pretty nice, pretty significant dielectric strength. Okay, now we have the Leyden jar shunt. So the Leyden jar shunt provides the electrical connection between the 2 capacitors, the 2 Leyden jars, and to complete the circuit, since without it, the Leyden jars would not do anything. Now, these can be removed and disconnected from the Leyden jars easily to help demonstrate what capacitors do. Now, this picture is one that I borrowed from online since I have not made my Leyden jar shunts yet. I'm still in the process of figuring out what's not going right with my Wimshurst machine. Okay, now the big question. How does it work? You know, that's a great question, you might ask. So first step in the Wimshurst machine is the charging step. So the vents begin at any one of these sectors. Well, these sectors will, at least one will almost always have an unequal charge, an unbalanced charge, you might say, as long as they're dry and clean. If they're wet, that means that the charge will dissipate into the humid air, and then it would become uncharged. Let's just say this sector here on the front has a net negative charge. And then through the process of electrostatic induction, the sector opposite of it is induced so that the positive charge is facing it, and then the negative charge is repelled away towards the far back. As you can see right here, the charges are separated. And then the Wimshurst machine is called an influence machine because the charges are influencing other charges. And now we have, okay, and then we can see that there are neutralizing bars on both sides. Now let's see what they do. So what we need for the neutralizing bars is we need to neutralize the charges. So since there are 24 sectors, which are even number of sectors, a neutralizing bar would always touch 2 sectors, 2 opposite sectors, as you can see right here, at all times, or touch no sectors. And although, let's start with this, this backside, right? We can see that the front sector is what we just looked at. And now let's rotate to the backside and look at the influence sector. Now, this sector originally had a net 0 charge. It was neutral. But since it was induced by the front sector to have a charge separation, this neutralizing bar, in fact, sees only the bunch of electrons on the surface. And since there's electrons, well, then it would want to flow because the electrons want to be separated from the other electrons from the front of the metal sector. Now the electrons will flow through the conductive neutralizing bar onto the other sector. And this is just the rare view, but it occurs on both sides of the Wimshurst machine. And now this other sector will in fact become charged, and this sector will also have a net charge. So what happens is that this sector would become would have a net positive charge, and this sector would have a net negative charge. Now, what happens after neutralizing? So then let's see. Well, these metal sectors are no longer neutral, as I just explained, and now the disks will continue to rotate a bit, right? It will rotate past, and then this is the picture or the scenario of immediately after the previous events. Now, what happens from now? Basically, we have more charged sectors now, and everything just repeats all over again. The newly charged sectors influence more uncharged sectors, and then the uncharged sectors become charged. They influence more uncharged sectors, and eventually everything becomes charged. And you can see that an interesting fact is that facing sectors on the front and back panels, the disks, actually have an opposite charge. And now you can see everything becomes charged. And you notice all of the negative sectors move to the left collector, and all of the positive sectors move to the right collector. And from the rear view, that's also true, since these are counter-rotating disks. And then all the negative would move to the left collector, and all the positive would move to the right collector. Now, this isn't true for all Wimshurst machines, because for example, you could have the initial charge sector be positively charged. But we do know that all the negative sectors move to one collector, and all the positive sectors move to the other collector. And then these collectors neutralize the sectors again.
Will, if you have a question, you can just speak up.
Oh, Will has a question?
Well, yeah, it's just, isn't it not the left collector when you flip it around? Isn't it now the right collector?
Okay, so yes, to specify, the left collector means the left side from the front view. That's basically what I mean. So if we call this left collector collector A, and then the right collector collector B, then we know that from front or back, all the negative sectors are moving to collector A, and all the positive sectors are moving to collector B. Does that make sense, Will?
Yeah, I get it.
Okay, perfect. Now these collectors, as I said, they neutralize the sectors, and the process restarts all over again. And this will just continue on as long as you're cranking this handle. Okay, now, okay, I have two duplicate sides. Let's skip over this one. So what do the collectors do? So actually, how do the collectors actually neutralize the charge? Because they don't actually touch the sectors. You can see that there's a tiny air gap here. Well, it utilizes something called corona discharge. Now, how this works is first, the sector repels the, let's just say this sector is negatively charged. That means in this diagram, this would be the left sector, the left collector. So if the sectors arriving are negatively charged, that means it would repel all the electrons out of these collector combs somewhere else. And since this is a pretty long electrical circuit, it does have places to go. So it would repel. Now that means that these points would become positively charged. And since they're very, very sharp points, and as we learned last year, electric fields are strongest where it's pointiest. That means that very, very strong electric fields will form at these points. These electric fields will ionize the air, also known as, it would make the air a corona. And this would help make the air conductive. And that means the charge would flow from the sector onto the collector points, therefore neutralizing the sectors. Now you can see a picture of my Wimshurst machine and comb working. I took this on a pretty long shutter speed, so you can actually see the ionizing and corona discharge happening. The same thing happens on the right collector with the positive sectors. Now, where does all this charge go? So this charge goes to the rest of the circuit. So we first have a spark gap. The spark gap is very similar to the one that I had in my Tesla coil if you saw my presentation from last year. It's basically a mini capacitor with a pretty low breakdown voltage since air is not a great electrical insulator. And that means the spark gap would break down before the Leyden jars. This would cause all the charge stored up in the Leyden jars to form a charge dump across the electrodes in a big zap. Basically, the collectors are a power source. If you look at this circuit right here, you can see that the collectors are basically a power source. And the spark gap is a fast switch to discharge the Leyden jars, which are capacitors. As we practiced with the circuit board last year in Physics 2. And now this shunt can be disconnected, which disconnects, you see these red lines, it disconnects the Leyden jars. Actually, the shunt is connected right here, so this diagram is drawn incorrectly. Disconnecting this shunt would disconnect the capacitors, meaning the capacitors would not do anything. And then the only charge dump that would happen is from the capacitor between the spark gap, since the spark gap is essentially a tiny little capacitor, since it does have two conductive surfaces and a dielectric in between. So some problems that I faced. There were a lot of problems. First of all, my discs were wobbling significantly. They were rubbing up against each other. So basically how I fixed that is I used hot glue to compensate for the imperfections in my 3D printing. And then I used hot glue as little spacers to adjust the angle of these bearings inside of these bearing holders. As you can see, it fits in here, but if it's not perfect, I use hot glue to compensate. Next, it was producing a maximum voltage of 200 volts. Which is nowhere near the 67,000 required volts to make a spark happen. So I proceeded to use the staring at it and make it work problem, the method, for 30 minutes. Actually, I think it was longer than that, since but at one point I was staring at it for 30 minutes, and I realized something. I realized that there was a conductive steel rod connecting the two neutralizing bars. Now let's think about this. Why would this be a problem? Well, let's go back to the to this diagram. Yes. So if we look at this neutralizing bar would have electrons flowing up. The electrons would be flowing up since these are positively charged sectors and would repel. And then these would have electrons flowing down. But that doesn't prevent the electrons from flowing across the sectors. That would mean that all four of these sectors would effectively have the same exact charge because of the conductive steel rod connecting these two sectors. Now that's a problem, since that would mean it would produce absolutely no voltage. And the only thing that would help it produce voltage is effectively the resistance in the steel rods, and steel is a pretty resistive material. Now, how I fixed this was I moved on to Gen 2 of my neutralizing bars. I wrapped a bunch of electrical tape around it, as in a previous picture. That didn't fix anything. It was still generating only 200 volts. So, and then I thought to myself, well, maybe since the electrical tape is only rated at 600 volts, perhaps it's because the electrical tape was not working. So then I proceeded to move on to a different material for the steel rod, the acetyl homopolymer. Now this is a plastic, it's very non-conductive, so theoretically it should fix the problem, right? Well, no. In fact, it made it worse. After I replaced it, it was generating only 60 volts instead of the 200 volts as previously. Now that was a big problem. And I had no idea where to go from there, because all my logic was just didn't work. So that's bad. So let's see. Well, perhaps I thought maybe the problem is with the charge collectors, since you can see that there are some professional Wimshurst machines that have only 2 points on the charge collectors, and I had around 12 points. maybe the problem is with that. And also, since my charge collectors are made out of copper and pretty flexible, I did bend the charge collectors away from the charge sectors. And to a point, it did increase the voltage, because originally it was 60 volts and now it produces 200 volts. But then if I keep going further, the voltage would drop down to 0. So that could be a problem, and I'm not sure. So that's basically my next step. My next step is to redesign and reconstruct the charge collectors. Yes, and now we have time for a demo. This is my finished design, and I have a voltmeter hooked up to this charge electrodes right here that are using alligator clips. And since the current is very low, like milliamps low, I can use alligator clips. Now, I hope we can see this clearly. Yes. Now, if we start cranking this thing, you can see that it does in fact generate some voltage. And if I go very, very fast, what's the voltage at? That's around 200 volts or so. So you can see that it does generate some voltage, but not nearly enough. And if we move closer here, if I can move this camera and don't make everyone dizzy. Oh, that's not good. I guess let's just put it here. So basically, you can see that here we have the charged brushes for the neutralizing bar, so that it would neutralize the sectors. And I thought maybe it was because the neutralizing bars aren't touching the two sectors at the same time. Well, actually, they are. You can see right now that they are contacting opposite sectors. If you do count, that is the 12th sector away from this one. So that isn't the problem. And yeah, I have no idea what the problem is. That's the summary. And yeah, and also to demonstrate again, these two O-rings this front O-ring is twisted, as you can see my little diagram to remind me right here. And basically it helps the discs rotate opposite to each other. Both of them rotate clockwise. Okay, that's my presentation. Does anyone have any questions?
I don't know.
Stephen, it's been 33 minutes.
Yeah.
Your throat hurt, Stephen, from talking that long?
My throat hurt? No, not exactly, no.
Okay, well, that was very long. If we have questions, maybe we'll have to tell you later, Stephen. But one thing I will say to you is you don't have the Leyden jars hooked up because the shunt's not in?
Yes. Yes, I could probably talk about that.
No, you did. Don't talk about it. But the point is, it's not going to generate that much voltage without Leyden jars.
Well, actually, here's the thing.
I'm just saying from actually using them, if you take that out, it won't generate anywhere near as much voltage.
No, it's the current that's different. The voltage would be the
I'm
same.
telling you, like, I've done it and I've taken it out. The voltage is nowhere near as high.
Well, I've also done it and I've taken it out, like with an actual Wimshurst machine, and it generates.
Yeah, I did it with the one in the classroom.
It generates with the same voltage, but just.
How did you measure the voltage?
Using how far it can jump across the gap. It was.
Yeah, that's what I did too, and it was nowhere near as much.
That's interesting. I used the Wimshurst machine from the Carnegie Science Center, and it.
Maybe theirs is better.
I'm not sure because theoretically, if you look at my diagram, if you look at my diagram,
bring it up. We got to go on because everyone else has to go still. But I'm just saying, I would try to get that working and then worry about it. Okay.
Okay, fine. But if you look at this diagram, like if disconnecting it won't change the voltage at all. It would just change the current of the charge dump.
It changes the amount of charge you can store. I totally understand and believe.
Yes,
what you're
exactly.
saying. But what I'm telling you is, in my experience, it has changed the gap.
Well, okay, we can try that. I mean, my next step will be to make the Leyden jar shunt to make a big zap, as Jason Masco is saying in the chat right now. And I would also probably modify the charge collector cones. I hope everyone enjoyed my presentation. And I'm glad that Josh didn't actually fall asleep.
It was Will anyway.
Oh, that was Will?
Yeah.
Good.